Okay, hey guys, welcome back to I'm going to call week 5 of your environmental chemistry course. Week 4, we had an early Eid break happen, so I'm calling this week 5 for us. So if you are looking for classes or online lectures for week 4, they do not exist because when the early Eid break was announced, we missed 2 of our classes that week. So this is an exact continuation of what we did way back in May, middle of May, in week 3. We were into chapter 2, about halfway into chapter 2, the biggest of our chapters, and we started talking about different properties of water, and one of those being temperature. So we talked about biological oxygen demand, dissolved oxygen, and then the last one we got into was temperature. Now, if you go back and look at the YouTube video, or if you can remember 3 weeks ago, I can't, we almost finished temperature. I got towards the end of this. So one thing I'll say before I get into the new stuff is this is what your lab is on this week. So the lab this week is about temperature changes. And I just got a message in the chat. That's no problem. So someone's having problems connecting, and again, no problem. Whenever that person can connect, that's okay by me. And again, if any of you guys have problems connecting, if your internet I had a student last year forgot to pay their internet bill and their internet went out. It doesn't matter because you can always join back when it happens. He was back within like 15 minutes. I think he called a redo. But you can also check this out on YouTube. So, all right, let's get going. So your lab this week is on temperature. And you can see me, if you haven't watched the lab yet, you should, because it is due tomorrow, but it wouldn't take you too long. The video is the longest part. Once you've watched the video, the write-up is pretty quick. You can see me in my kitchen looking at temperature changes. So I'm heating up water and looking at, it's been a week for me now. I looked at dissolved oxygen and carbon dioxide. And because I was checking carbon dioxide, I also checked pH because they're directly related. And I think we're going to get into that today. So I know it's been a few weeks, but if you guys can remember this is one of the slides I showed you. Temperature affects almost every water quality parameter that we're going to study in this course. Dissolved oxygen we've already done, which is directly related to the oxygen demand, but it also affects things like photosynthesis and metabolic rate. So photosynthesis being, what the plants do to create oxygen in the water. And then, of course, metabolic rate, that's the amount of oxygen required by aquatic life. The higher the metabolic rate, the more dissolved oxygen they typically require. It also affects things like salinity and conductivity, which we'll talk about a little bit later. And then, of course, on the bottom there, excuse me, temperature definitely affects CO2 and pH. So in the lab, now, is this going to let me write? Yep. Ooh, okay, that's nice. In the lab, I'm looking at dissolved oxygen and carbon dioxide, which is related to pH. So we talked about all of that. Oops, sorry, and I showed these slides. I was just looking at my YouTube video to see how far I got. So maybe I'll do a little quick review of these few slides and then we'll move into pH, okay? So if you've already seen this, or if you're coming into this video from the last video, I might repeat myself a little bit, but I haven't seen you in a few weeks, so maybe it's not that bad of an idea. So as this slide 76, this is just a text version of this slide. And this is usually the point of this slide is when I have actual classes and I print the notes, this picture can be very hard to read. So this slide is a little bit easier when you're studying. So the slide 75, 76 here, they are the same. It's just one is text and one is a picture. So, and now I'm thinking of questions I could have put in your lab, but I didn't, but this is a good question. As temperature increases in water, studies have shown there's a direct relationship here between metabolic rates. And I mean, this is common sense because you think about you guys, I say you guys, I mean, even anybody in this country, as the summer is coming, it's getting hotter and hotter. And I know personally, I'm spending less and less time outdoors exercising, say, in the middle of the day. So just imagine you're out at the Corniche or in the souk and you're walking around in December or you're walking around in June. In December, in the winter, we'll call it, you can spend a few hours. The weather's nice. It's okay. You're not getting warm. You're not breathing fast. You're not sweating. It's comfortable. But in June or July, when the temperature is above 40 degrees, you would be breathing heavier, breathing faster, you'd be sweating. I want to call it the rate of your body would be accelerated. And I don't know if that's the right term, but your breathing would be faster. You'd be sweating a lot more. And it's because of the temperature of your body. You're trying to cool yourself off by sweating heavily, breathing heavily. Heart might beat a little faster as well. So in the water, when the temperature gets higher, same thing can happen with aquatic life. Their metabolic rates can rise a little bit faster. So their need for oxygen might be a little bit higher as well. Photosynthesis is also affected by temperature in general. And this is a really interesting graph over here on the right. In general, temperature does affect the photosynthesis of plants, but there is a maximum. So you can see the graph starts to go up, but after 30 degrees Celsius, or it depends on the type of aquatic life here, but after a certain degrees, once it gets too hot, the photosynthesis begins to slow down. So there is a region here where photosynthesis can be maximized. But if it's too hot, and you can see here 40 and onwards, which is kind of what we're seeing in Doha now, photosynthesis will decrease. So things like, again, this could be wink, wink. I know you can't see me, but a question about, things that are affected by temperature. Plants and aquatic life, or, animals or whatever you want to call them, are affected. Metabolic rate, photosynthesis both affect plants and animals in the water. This is based, I don't know if I did this one last day, but this is kind of what we're doing in your lab this week. I'm basically taking a sample of, I use tap water this week. I don't mess with the bottled water because I didn't have time. Well, I had time, but it would have taken a lot of work, I guess, to do all the trials for all the water. And if I was in the lab, it might have been easier, but the kitchen isn't ideal. So in the lab this week, I looked at heating up a sample of tap water on the stove, on my oven, stovetop, and I measured the dissolved oxygen. And you can see from this graph here, this again will definitely be a test, or well, no test, but quiz, online quiz question, wink, wink. Definitely a question for you is the relationship between dissolved oxygen and temperature. And you guys actually answered this in lab number 2 a little bit. As temperature increases, the solubility of gases decreases. The molecules are moving faster. They can leave, turn into the gas phase, leave the water a little more readily as the water gets warmer. The molecules move faster and faster and faster, so they're not as soluble in that solution or in the water. I mentioned that earlier, so I won't spend much time on that, but you can see at 0 degrees Celsius, the DO level in ppm is around 14. In 25 degrees Celsius, it should be around 8. Okay, and it continues to drop as it gets warmer and warmer and warmer. All right. One of the questions on the lab number 2, was would fish be able to survive in our samples of water? And in theory, the answer is yes. And I think a couple of students said no. The aquatic life, most fish would be completely fine with a dissolved oxygen content of around 8. And I think if I can remember correctly, the bottled water was like low 8, 8.1 or something, 8.3. And the tap water was a little higher, 8.7, 8.8. Tap water tends to be a little bit higher, especially when it's cooled, because when you open the tap, the water is pouring through these pipes and it's pouring out of the tap, and it can get oxygenated just a little bit slightly. When it leaves the tap, it's mixing with air. Think about bottled water. You know, when I open the bottled water, it's interacting with the atmosphere, and I'm gently pouring it into a beaker and it's interacting with the atmosphere. I put the lid on. When I took the tap water sample, I poured it out of the sink, you know, out of we call it a tap. I don't know if you guys call it a tap, but out of the faucet, if you're British. And when it's coming out of there, it can get aerated and add a little bit of air, which, you know, does have oxygen in it. And that's one of the reasons. There's a few reasons, but that is one of the reasons why the parts per million of the tap water was maybe a little bit higher. It was, again, high 8 versus low 8. But yeah, the answer to the lab question was yes, in theory, it could support aquatic life. There's much more factors that affect aquatic life than just dissolved oxygen. But in terms of the dissolved oxygen, yes, 8 is enough. All right, this is another good question, or a good thing to know, is factors that influence temperature. So things that can influence the temperature would obviously be the sunlight. So in the middle of the day, the temperature would be higher. The atmosphere, and I mean the atmosphere here, I basically mean okay, first of all, I'm talking about the factors that influence the temperature of the water. And here by atmosphere, I do mean temperature. And I know that seems kind of silly or common sense even, but what I mean is if the air above the water is warm, then the water below will likely be warm. Now, it depends on the volume of water, the motion of the water. There's a lot of factors here, but typically, you know, look at Doha. If it's 50 degrees in the air, the water will be a little bit warmer than, say, in the winter or in the nighttime, when it gets down to, say, 20 or 30 degrees. Turbidity is another factor that influences temperature, and we'll talk about that later. But turbidity basically means the cloudiness of water. Water that looks kind of gross, the word murky, it comes to mind. That is turbid water. So that can block sunlight and lower the temperature. We'll talk more about that towards the end of this chapter. I love this, confluence. Confluence is a fancy word. It means the junction of two water sources. So, you know, a source of warm water flowing into colder water can change temperature. Cold water, you know, think about, this is just an example, but if you had ice runoff in the winter, so from the top of a mountain, the snow and ice are melting and it's running down the mountain. As altitude gets lower, I think I'm saying that right, you know, you get to the bottom of the mountain, temperatures are usually a little bit warmer, but the cold ice water hits the warm water. You know, these can influence, that can influence temperature quite easily. And then, of course, you have the human-made anthropogenic. I'm not going to write that word out, but maybe I will. Anthropogenic oops. You might get a question about anthropogenic things later, so it's good to know. Anthropogenic means human made. It says here man-made. Deforestation, you know, getting rid of things like even blocking sunlight, the trees that block sunlight. If you get rid of that, it can change temperature. Thermal pollution, we'll talk about that later. But a lot of industries might use water for cooling systems. And, you know, as you're running, so they kind of run cold or cool water through the plant, and that water gets warm, but it carries the heat away from equipment. Well, that warm water sometimes can be dumped into a water source. It's called thermal pollution, not good. And impoundments, things like water dams, where we've built structures to control the flow of water, that can influence temperature as well. So guys, happy face on this slide, because you might see this slide or this information again. Okay, sorry, just seeing how much left. Excuse me. So what does all this mean? And this could be another type of question. I might, you know, ask you, what are some things that affect the temperature of water? But then I might say, well, what does that do? Is it bad? Is it good? What happens? And typically, anytime you change an ecosystem from its kind of natural state, I want to use the word equilibrium, it's typically a bad thing. So water that is too warm, and again, humans can have a big impact on this, is considered to be more dangerous than water that's cold, or I don't want to say too cold, but cold water. Typically, natural water sources are pretty cold. And if you've ever been in swimming anywhere in Europe, you know, or anywhere that there's a pond, lake, river, stream, no matter what time of year, no matter what temperature out, it's typically pretty cold. But, you know, water that gets too warm can definitely be dangerous to aquatic life, because it can affect, well, first of all, metabolic rates. If they get too high, the animal, the aquatic creature, can become stressed and die. These things, long-term consequences of temperature change, can affect the growth of these things, can affect things like reproduction, can affect things like how they can tolerate diseases, and their just in general survival rate. It was my brother's birthday, May 30th. I have two brothers, and one used to work here for many years. He just moved home. Well, my other brother lives in where I'm from, you know, around home, I'll call it. And he is a manager at an aquaculture facility. So in simple terms, he works at a fish farm. And if you've ever heard of fish farming or never heard of fish farming, it's basically like farming, you know, but they grow fish and they raise fish from, you know, the eggs to a size where we eat them, right? So some types of fishing aren't sustainable. So fish farming is a way. There's controversies around it. We won't get into that. Me and my brother, we talk about it all the time. But the idea of fish farming, besides obviously making money, is sustainability of some of the fish we eat. So my brother, for example, grows salmon. And anyways, the bad news, he's not as busy this year as he is normally. They lost, I think it was over 800,000 fish. So they grow, I say grow, it sounds weird, but they raise millions and millions of fish every year. They kind of follow the natural cycle. So this is the time where they would take these small fish from the plant. They're kind of grown in, I say grown, that's such a weird thing. I should be saying raised in a plant, like in, you know, a big building. But after a while, that's not really good or sustainable or normal for the fish. So they move them to natural water, and they finish growing or being raised in natural water. Anyways, something happened, and this is kind of part of my brother's job, is where he lives has a direct link to the plant, the you know, big building where they raise the fish. And he has all sorts of computers and information in his home that monitors things monitors the water for changes like pH, dissolved oxygen, temperature, et cetera, et cetera. Something happened. I didn't ask because it was his birthday, and I didn't want to get into bad work talk on his birthday, but something had happened with the water quality, and they lost 850,000 fish, 850,000. So almost a million fish died. When I say died, this can happen naturally as well. This happened naturally where I'm from. Again, there was a warm water weather or temperature anomaly that happened off the coast of Newfoundland. That's where I'm from last year. That also killed a million fish. So, I mean, just these little changes, they can be natural changes, like warm water coming, from, I guess, the Gulf of St. Lawrence, if we're talking about geography. But, natural things like a rush of warm water, or they can be things that like very small that happen, like in my brother's plant, maybe a piece of equipment malfunctioned. But these little tiny changes of things like pH and temperature can be devastating to aquatic life. So anyways, little side story, but it's interesting. And it's something my brother kind of deals with every day at work. All right, so the bottom little note there, it says each fish species has its own comfort range, just like humans have their own comfort range. Think about the temperatures humans usually thrive in. So, anything around 20-ish, I think for me personally is a good temperature. But when you get below 0 or right now above 40, things get a little uncomfortable. And the same thing is the same for plants and animals. So here I have a little chart. I don't know how well you can see this, but of different types of fish and the temperature, kind of temperature ranges, maximum temperatures for different things. So the bottom two are for spawning. So spawning is kind of like the reproductive process where, they're reproducing to make new fish. And you can see the max temperatures there. It depends on the fish. Atlantic salmon, you're looking at very cold, well, not very, but relatively cold temperatures. 5 and 11 degrees are the maximum temperatures for them to reproduce. And then for the survival, for growth and survival, you're looking, this guys is maximum. You're looking at 20 to 23. Some fish, like the bluegill, the temperatures are a little warmer. These are fish, obviously, that are grown that thrive, I guess, in warmer water. But anyways, you don't have to memorize this graph, but every fish has different maximum recommended temperatures. And if you go above these temperatures, obviously not good, right? Outside of the comfort zone for the fish, they might not spawn. And if they did spawn, and again, when I say spawning, I mean basically reproducing. If they didn't spawn, they had more fish. It's kind of weird, but if there were fish, they might not survive. So big consequences of temperature changes, the spawning or reproduction of fish or the survival rate of those fish. Now, water can also be too cold. So this is kind of a good little quick point to know. If I don't know if you've ever heard of the parable or story Goldilocks and the Three Bears, but the idea is there's kind of like this perfect range of temperature for most creatures. And if it's too cold, again, if you've ever heard of Goldilocks and the Three Bears, you'll know what I'm talking about. If it's too cold, it's not good. If it's too warm, it's not good. What we want is kind of in the middle. So water that's too cold can slow down metabolic rates to be too slow. It can slow down biological processes. It can be, detrimental or bad for the aquatic organisms. If it's too warm, it can cause excessive respiration, so the metabolic rate goes up. Fish can become stressed. Again, it can harm the aquatic life. And this is an important little note down here. Water that's too warm can, there's multiple issues here, but another big one is, first of all, the fish are stressed, they're breathing faster, they have, increased metabolic rates. But warm water doesn't have as much dissolved oxygen. So the biological demand for oxygen goes up, the dissolved oxygen gets lower, the amount of dissolved oxygen gets lower. These are all kind of related here to the biological oxygen demand, BOD. So temperature goes up, respiration rates of fish get higher, but the dissolved oxygen gets lower, so the demand for oxygen is too high, fish die. I keep saying fish, I mean aquatic life, but kind of same. So that's temperature. That's kind of what your lab this week is on. I definitely want to do pH today. And we'll check about nitrates and phosphates a bit later. Sorry, I'm skipping ahead here to see what's coming up. Oh, okay. I think maybe this week we might actually get to turbidity, which would be great. All right, sorry. I'm just kind of trying to see what's coming up for the next couple classes. All right, so let's do pH today. I'll check the time after pH. Yeah, we'll see how we're doing after this. The reason I'm definitely doing pH right now is because in your lab tomorrow, again, if any of you have watched the video, I talk about pH in your lab tomorrow, and I measure the pH using a pretty okay pH meter. I took one home from the lab at work, so it's not the best, but it's not one of our high quality ones. I kind of took one that they wouldn't mind me borrowing for a few weeks. So anyways, this will kind of link into the lab video. It's only a tiny part of the lab, so that's why the lab is due tomorrow. Lab is basically covering dissolved oxygen, but anyways, here we go. So we're going to look at a few very quick outcomes. The lower the pH, the more acidic the water. You guys know that from Chemistry 1200. We'll talk about how acids form in the water, talk about pH ranges of the water, and then the effective temperature on water. And I definitely want to get to this today because this is in your lab. All right. So, easy, right? Chemistry 1200, or I mean, this is junior high school chemistry. Solution pH under 7, acid. Solution pH over 7, basic, easy, no problem. Not going to spend any more time on that. Now, excuse me. If the pH is too high or too low, again, I talk about this Goldilocks zone. Goldilocks and the Three Bears. I was actually talking about that with my cousin the other day. But this Goldilocks thing, this zone, is for so many things. Temperature, pH, this comfort zone exists for all creatures. And pH is one of them. And yes, I just got a message. No problem somebody just joined us late. No problem. Remember, if you're late or you miss a bit, all of this will be on YouTube. So again, no problem. All right, so back to Goldilocks and the Three Bears. If you've never heard of it, I'm sure most of you have, but this woman breaks into a bunch of bears' homes or home. These three bears are living in a house, and they have porridge. And this blonde lady, Goldilocks, she breaks in, and which she shouldn't have done, and she eats their food. And one of them is too cold, one of them is too hot, and one of them is just right. Anyways, I think in the real life story, if you look into it, I think the bears actually eat her at the end. Not in the one you might have been read as a child, but I don't think it ends well for her. So you don't break into people's homes. But the chemistry point of the story is she ate the porridge that was the perfect temperature. It wasn't too hot, it wasn't too cold. We just talked about temperature, but pH can kind of have that thing as well. It can be too low, it can be too high. We're looking for pH to be just right. And I know us as humans, we're not in the water, but our blood has a pH level that can be too high or too low. My respiratory therapy students talk about this all the time. There's acidosis and alkalosis. And things like diabetes or smoking or so many factors can affect the this in people who are vulnerable. So acidosis or alkalosis, meaning your blood can be too low, pH, or your pH can be too high. It can be fatal, right? It can kill people. And breathing, respiration, is a way to control the pH of your blood, just like the buffers that are in your blood. And this is all kind of chemistry that you might have learned a little bit before. So what I'm saying is, even though we're not in the water, we have a specific pH range. Our blood specifically has a specific pH range where we function. And outside of that range, it can affect with, enzymatic activity or the enzymes in our body. So again, all of this is not good if your pH leaves the Goldilocks zone, the good zone. And the same thing happens for fish or aquatic life. So pH too high, too low, it can kill your fish. And this is commonly, from my experience, something that can affect fish that you might have in an aquarium at home. If the pH of your water isn't controlled in an aquarium, your fish will die. pH can also affect the solubility and toxicity of chemicals and heavy metals in the water. So if they're more soluble, it's dangerous for the aquatic life that's in there. The majority, put a little smiley face here, the majority of aquatic creatures would like a pH range of 6.5, which is, I think, around where our blood would be, slightly acidic. Or are we slightly basic? I gotta look that up now. I can't remember. It's been so long. But our blood pH is near 7. And these aquatic life can survive actually up to about a pH of 9. So into the basic range. So, you don't have to memorize that number, because you can do your quizzes with your notes open, because they're all online. But just know that the acceptable range is around 7 to 9. Okay, but more specifically, I guess it could be slightly acidic, but not much lower than 6.5. Now, this is, first of all, this source on the bottom is where I get a lot of my images for this, or for these notes. This is the single best source for this chapter that I've found on the internet. It is amazing, like amazing. And without this source, a little heart there, I would not have half of the graphs and pictures that I have right now. So if you ever want to read more about this, that source on the bottom, Fondriest, amazing water quality source. It's amazing. So they provided me with this picture, well, their website did, of kind of like acceptable ranges. So I know it's a little hard to see, but like blood, for example, where you draw a line down. So there's like the acceptable pH of blood. If I'm drawing that line straight, it's slightly basic. I think 7.35 rings a bell now that I'm thinking about it. Plants, you can't really see the edge of this, or on my computer screen I can't, but plants, you're looking 6.5 up to 12. Plants don't necessarily mind a little bit more of a basic environment. Humans in general, not talking about your blood specifically, but humans anywhere from 4 to 10, we seem to survive. But here, above 10 and below 4, fish can die. Okay, so the range here is typically towards the neutral range. Fish prefer this range here. Okay, but they can survive with it being a little bit more acidic, and anything below 4 or anything above 10, they will die. But again, their preferred is still 6.5 to 9. That would be their ideal range. So here we go. Here's a bigger picture. I should have been drawing on this one. It's a little blurry, but you can see again the ideal kind of range here for the fish. All right, and plants. Cool. So you might be asked about this a little later. Just like, guys, I can't stress this enough. When you're doing any of your labs or any of your online quizzes, just keep your notes open. If you have a printer, that's great, but if not, maybe on your phone, or if you have a, you can borrow someone's tablet, keep it open on the side, open a new tab, whatever, but keep these open. Okay, so I'll talk about pH, factors that affect pH, temperature, because that's what your lab is on, and then I'll check the time. I don't even, hold on guys, I'm just gonna grab my phone. I'll be right back. Okay, sorry. Okay, so it's 10:20. I'll just do a little bit more. I'll finish pH, and then I think we'll pretty much finish it up there for today. So not too much longer. All right. So pH and dissolved oxygen. Little pH changes, still big effects, right? Anything in the water, any type of change to the ecosystem can have very long-term effects. So temperature, pH, dissolved oxygen, all of this. And they're all slightly related in a way. A slight change in pH can increase the solubility of nutrients, making them more accessible for plant growth. We'll talk about this in the literally in the next section. But, you know, this is not necessarily a good thing for the other aquatic life. When you mess with the food web, the food chain, well, I guess chain's not the right word, but the food web, it can have really bad effects for other things and really good effects for some other things. So if the changes in pH make the food of phosphorus, the food of plants a little more soluble. I call it plant food, I mean nutrients. Plants can grow. That might seem to be a good thing, but overgrowth of plants can be very, very dangerous and detrimental, harmful to the aquatic life. You might have heard of algal bloom before. We'll talk a little bit about that later. This, you know, overgrowth of plants in water is not a good thing. So this is the fancy word. This is not in your course outline, but when you see this oleotrophic, I can never say it. I should look up how to pronounce it before I make YouTube videos. But basically I'm talking about, and this is again, not in your course outline, this word, this term, but in a lake low in plant nutrients and high dissolved oxygen levels, there can be a chain reaction into the food web. So if there's too many nutrients, or if there's too few nutrients, it can cause a chain reaction in that ecosystem and can have detrimental effects to everything in it. So again, it's this whole Goldilocks thing. Everything needs to be kind of managed at a reasonable level. So if the nutrients are more accessible, plants can thrive. This increases the BOD. Oops. Remember, BOD, biological oxygen demand. And if there are a lake or a water ecosystem, that has a lot of aquatic plants and algae, they're thriving, they're growing, the biological oxygen demand gets higher, you can create something called a eutrophic lake. This is a lake rich in nutrients and plant life, but low in dissolved oxygen concentrations. Other organisms suffer again. So this can all happen with changes in pH. pH can affect the solubility of nutrients. If the nutrients are too low, plant lives will suffer. Remember, plants are responsible for dissolved oxygen in the water. They're one of the two things that we talked about. So if the low nutrients, low plants, low dissolved oxygen, things are going to die. Too much nutrients, there's too much plants, it can increase the demand for dissolved oxygen. We'll talk about this a little later. Things can die. So pH needs to be managed. Excuse me, guys, I don't know, I'm losing my voice here. pH needs to be managed in these ecosystems into an acceptable range, or it can affect pretty much everything in that water. So a minor increase in pH levels can cause a lake to be rich in dissolved oxygen, excuse me, and it can make it become eutrophic, meaning, or it can make it become eutrophic, lacking in dissolved oxygen. Sorry. So changes in pHs can make make a lake become rich or lacking in dissolved oxygen. Just the pH levels can affect this. So this should say change, sorry. Oops. All right, there you go. And I got two pictures here. One of the big reasons for a eutrophic lake, you see all the green here, can be anthropogenic. It's typically when when a plant life explodes into a lake, typically it can be human influences. Like a very common one, or one on the top of my head at least, would be using fertilizers in agriculture. If these fertilizers are washed off into a water supply, those fertilizers are plant food. And if the plant food gets into, a river or a lake or a pond, for example, the plant life can explode. And this creates a eutrophic lake, which is lacking in dissolved oxygen. Remember, guys, these terms are not in the course outline, but still good to kind of know in general. So let me take a sip of coffee here. All right. Whew. So factors that affect pH, we'll talk about that. Then I'll get into temperature and I'll check the time. I'm super sorry. This is not the most entertaining video, but it's all we can do. So factors that affect pH. What would make it change in a water ecosystem, in a lake or river stream? Factors can be natural, factors can be man-made or anthropogenic. Most natural changes would be from rocks around it and other materials. Things like even like a volcano erupting, these are things we can't control, not yet anyways. They can change the pH of water around it. pH can also fluctuate with precipitation. And again, this doesn't need to be anthropogenic. Precipitation, the runoff of water, of rocks and surrounding rocks, that can affect pH. But something like acid rain and wastewater or mining discharges, water coming from industrial areas or mining, another industrial process, that can definitely affect the pH. These are your anthropogenic ones. Remember, when I say anthropogenic, I mean human-made. So anthropogenic causes of pH are usually pollution related. One of the biggest ones, I learned a lot about this when I was a kid, was acid rain. One of the best known influence of this. The term acid rain applies to any type of rain that has a pH of less than 5, making it, of course, an acid. Okay, so it's less than 5, it's an acid. Factors that, and this is I won't get too deep into acid rain here. This is a topic I talk about in another chemistry course, though, chemistry, I think 1120 or 1121. Acid rain comes from the reaction of, and you don't need to know this, you don't need to know where it comes from. But if you're curious, it comes from the reaction of water with nitrogen oxides, sulfur oxides, and other acidic compounds in the air, in the atmosphere, lowering its pH. Now, nitrogen and sulfur oxides, for example, are products of burning fossil fuels, or oil and gas, the combustion of carbon. The combustion of, I guess, petroleum. I don't know if I'm saying that right, but the combustion of oil and gas, burning of fossil fuels. That's what I should be saying. So these things like nitrous oxides, sulfur oxides, carbon dioxide, these are typically byproducts of burning fossil fuels or from mining or smelting operations. Okay, so human operations, usually industrial. These put these chemicals into the atmosphere, they mix with the water, then we get acid rain. So another factor that can affect pH, and we'll talk a lot about this one later. There's a lot of stuff here I mentioned we're going to talk about later, like turbidity. But once this course is finished and you're kind of looking at this chapter all together, it kind of fits pretty well. But another thing we will talk about a little bit later is point source pollution. And this is water pollution that comes from a single discrete place. Now, what do I mean? Like, you wouldn't call, let's just take the Qatar or even just Doha. Let's take this as our kind of experimental zone. Okay, so we're looking at just Doha, or yeah, I'll say Doha, not even the country of Qatar, but like Doha. Or you could even say West Bay, just take a part of this country and look at it. The cars in West Bay or the cars in Doha, when I say cars, I mean vehicles, any vehicle. You can't really call that a point source pollution because it's not a single discrete, what I used to say to my students is, I can't just point at the car that's causing all of the pollution. There's hundreds and hundreds and thousands of cars in West Bay that are all contributing. So that is a non-point source pollution. It's not from a single source. A point source pollution is like, I could go look at, now I know this is not in West Bay, but I could go look at a mine, an iron ore mine, where they dig for rocks, minerals, and point at that and say that is a point source pollution. There's not 1,000 mines in this small area. There might be 1,000 cars, but there's just the one mine. That is a point source pollution. Or again, if you took something like Al Sad, just the area of Al Sad, I could point at Hamad Hospital and call that's for biological wastes. I'm not saying that they're bad for pollution. Trust me, I'm not. But I mean, for biological hazards in Al Sad, Hamad might be a good example of a point source solution. It's a gigantic hospital full of sick people, and they would have a high source of biological waste that they'd be getting rid of. And again, I'm not saying that they're polluting, but I mean, that will be a point source, an example of I could point at a building and say, yes, this is where the pollution is coming from. So point source pollution is something that definitely affects pH, depending on the chemicals that are involved. Common sources, other point source pollutions that you could look at would be mining operations. And typically a lot of these things, we call this agricultural runoff. A lot of these things can be wastewater or industrial runoff as well. So sources of pH changes could be from mining operations and wastewater discharge. Soap-based products, so when you're cleaning things with detergents and soap and you let that water go out into the environment, it can be too basic. Mining operations typically have a lot of acidic runoff. A lot of the chemicals and water they use they can be acidic in nature. A lot of the interaction between water and rocks in general can produce acidic water as well. So mining operations, wastewater discharge, two factors that affect pH. All right, I think we're getting at the very end of this one today. I think double classes are kind of nice in person, but online it's a bit much. So I'll do this temperature thing. I'll just mention what's coming up next day, and that's it. All right, so we're looking at 4 or 5 more slides here, and that's it. All right, so temperature and pH. This is in your lab tomorrow. That's due tomorrow. So anybody just joining in, you do have a lab due tomorrow at 2. Very easy. The video, like I said earlier, is probably the longest part. It's about a 25-minute video or something, a bit long. Feel free to skip through it. You don't have to watch every minute of it. That video, you will need to answer some of the questions, and the questions are very quick. All right. So this slide here, or this section, will answer any remaining questions any of you have about that lab. Temperature and pH. Little reminder, pH is the number of hydrogen ions in solution. Hydrogen, H+, or more specifically in water, H3O+, hydronium ion. Okay, so this H3O+ is called hydronium, if you can't remember. At a pH of 7, so at a pH of 7, the concentration of hydroxide is equal to the concentration of hydronium. So the moles per liter of the acid is equal to the moles per liter of the base. I don't know why I added an E there to the word acid. Okay, so pH of 7, everything's equal. But when these chemicals, OH or H3O plus, are not equal, pH changes, okay? So as temperature increases or decreases, the ion concentrations also shift. I guess I'm kind of skipping something here. Let me just go back for 1 second. At a pH of 7, the hydronium and hydroxide ions have equal concentrations. Okay, so they're equal. And what's happening in water, I guess I should put this on the bottom, is water has this sort of equilibrium situation set up. Now, guys, you don't need to know this, so don't worry about it. Don't worry about memorizing or this or anything like that. But typically water has this equilibrium situation set up, okay? And if you've done chemistry 1201 or 1210, you've learned about equilibrium, and you've learned about K, the equilibrium constant, and you've learned about Le Chatelier's principle. And I'm not going to teach that again because I'm not really going to ask you about Le Chatelier's principle. If you can't remember, or you've never learned about this, I don't know, one of the two things, Le Chatelier's principle is a way to predict changes in equilibrium by the equilibrium equation and equilibrium constants. So we can look at how a equilibrium equation would change by, if we change things like concentration, pressure, volume, and temperature is a big one. Temperature is actually the only thing that affects the equilibrium constant K. All you guys need to know from all of this, and again, I'm kind of going a little fast through this because you did it in 1201 or 1210. All you need to take away from this is temperature affects all equilibriums. And temperature certainly affects this equilibrium. So as the temperature of water increases or decreases, that equilibrium also shifts or affects the ion. It also shifts and affects the ion concentrations, which can change the pH value. This is explained by Le Chatelier's principle, not something you need to worry about on a quiz, but it's kind of good to know that some of the things you did in 1200, 1201, 1210 actually matter for understanding something in 2770. So just if you can't remember, the definition of this is any change to a system at equilibrium will shift that system until it reaches equilibrium again. Okay, these chemical equations or equilibriums want to be in a state of balance where the forward and reverse rates are the same. So if you change an equilibrium, it will try to fight back and kind of reestablish itself. There's my, equation. The equilibrium for the ionization of water is exothermic. So if we increase the temperature of water, we would see this equilibrium shift left. You don't need to know this, by the way, okay? If we decrease the energy in the water, the equilibrium would shift right. And again, this is having an effect on my ion concentrations. So this is changing the pH of the water. If the temperature of water increases, the equation shifts left. A shift to the left would decrease the ions in the water, increasing the pH. All right. You don't really, okay, this is basically what you need to know right here. This. Okay, you do not need to know about Le Chatelier's, but you definitely need to know this. The pH of pure water will decrease as temperature increases. So, and I can't really remember what my numbers were in the lab, but if you watch that lab that I filmed last week, you should notice as the temperature increased, the pH should have decreased. And this lab was like realistic. It was done in my kitchen, but it was, you know, I used the best equipment I could. I used pH probes and I used the test kit, and I had a really nice thermometer. I measured the temperature of water at 20, 40, and 60, and I looked at the pH. And actually, now that I'm thinking about the lab, yeah, it was pretty close to this. Pretty close to these numbers, the lab. It was a little bit different because I'm using tap water, and I mean, everything's not perfect in my kitchen, but yeah, this is definitely something you want to know. The pH of pure water decreases, becomes more acidic as temperature increases. All right. Almost done here. No, I am done. Well, yeah, I guess I'm almost done. I am done. Now, typically, if it was a real class, I might actually do the next two, but the next two fit together really nicely. We're very quickly tomorrow, or Thursday, I should say, going to look at nitrates and phosphates. I'm going to do these two very quick, and hopefully I can get to carbon dioxide and turbidity, but we'll see. I'm not going to go too fast. But anyways, that's, I think, enough for today. This covers up to what you've done in the lab. You will have, I'm hoping, 5 labs, but I don't know with where we missed a week, but you'll definitely have 1 more lab, hopefully 2 more labs after this week's. And we'll look at a couple more water quality things in that. So guys, that's about as much, I think, as we can take today for the online. If you guys have any questions about this class, about the quizzes, about the labs, about anything, send me a message in the chat or send me an email. Other than that, have a great day, and I'll see you on Thursday. Remember, guys, the labs are offline. You can do the labs whenever you want. So when you look at your lab schedule, there's a lab tomorrow, but there's no class. You can use that time to maybe look at the other lab. I'm going to put lab 4 up tomorrow. Okay, have a great day, everybody. Any questions, let me know in the chat. Thank you, everybody. I have everybody, the people who are here, marked in as attended. So thank you.